So now what we would be doing is we would firstly be using for loops to find the dot product, and what we would be using is actually the formula that you would be more familiar with. So u dot v, let u and v be two general vectors. So u dot v is actually the magnitude of u into magnitude of v into cos theta. So I have already computed what the theta bit for uh, actually the angle between y and each of these x's would be. So the angle between y and x1 is 84.2894 degree. The angle between y and x2 is 56.3099 degree, and so on. I have already computed it, and now I would be using this formula and for loops to actually compute the dot product. And let me call this so first of all, what I would be doing is taking dot product using for loops. So here what I need to do is I want to, so instead of v I have a fixed y, and instead of u I will have x1 first, then x2, then x3, then x4, and I have already formed this matrix x which contains all these xi's. So how many dot products will I be getting is actually, let me call this dot product using loops as dpl. So I would eventually be getting 4 dot products. So let me initialize this to size x1. So my dimension is current section. So this is my dot product using loops, which is a 1x4 vector. I could have actually obtained this dot product inside and actually extended a list. So I could have done something like dpl is equal to an empty list, and I would have appended it, but this is more computationally efficient. Now what I want to do is I want to actually first loop over the x. So for that I'll do is for I is equal to 1 to size, and based on this notation uv, so u is x and its first row, and v would always be y. Now what I want to do is I want to find the magnitude of u and magnitude of v. What the magnitude of a vector is, it is like the element wise, it is actually the sum of element wise square of each of the vector, and then we take the square root. But since we would be, I said that we would be using only loops here, we would also be finding that sum using a loop. So magnitude of u is initially 0, magnitude of v is initially 0, and now I want to loop over all elements of u and v. Right now this u and v are two-dimensional vectors, so it appears easy and we may not want to use loops. We can just do like magnitude of u is equal to maybe u1 square plus u2 square, and then take its square root. So this is perfectly fine, but since we are actually developing a generic algorithm, sort of a generic algorithm for computing dot product, so we would actually be looping over it, and j is just the index, and actually we can think of j as u, or since it's just a simple vector, I can do null just actually gives the length of vector, and I know that actually the length of vector u and the length of vector v is identical, so I would not be actually looping separately, and I would just be looping here, or I can actually loop separately as well. So for finding the magnitude of u, what I do is magnitude of u is equal to what it originally is, and then I would be actually adding the square of relevant element here. And then what I can do is like k is I would also be performing similar stuff for v, make v is equal. So here I actually do the sum of element by square of respective vectors. I actually know that both these vectors have the same number of elements, so this would have also been possible, and this is actually more convenient. And here it would be j now, since j is the variable that we are looping on, and j would actually be, in the first instance it would be 1. So what we would be doing is that magnitude u is equal to magnitude u, where magnitude u is right now 0. So 0 plus u of 1 square. So what is u of 1? It is actually 0.5, and 0.5 square actually gives us 0.25. And similarly it would be for mag v is actually x-axis, yeah, so it's 1 0, so it would be 1. We can really see what's happening here, so I'll actually try to print it. So done with that, and once this summation has been done, what we want to do is we take its square root. I don't think I want to print that. And now my dot product using loops, and when I is 1, I want to find the dot product between y and x1, and I want to put it at the first index in dpl. So it would be dpl I is equal to magnitude of u into magnitude of v into cosine theta. Actually, just a slight correction, since the angles are in degrees, so the function for finding cosine in degrees is actually cos t. And let me run this. Yes. So here what I was telling is, it has actually printed it inside this loop. It is printed what is happening inside this loop. So magnitude u was actually 0 plus 0.5 square, which was this. Magnitude of v was 0 plus 1 square, which ended with this. Then magnitude of u was 0.25 plus 5 square, which resulted in this, and it was like 1 plus 0 square, which was this. But since I don't want now this much printing, and let me print just the dot products at the end. So what is the dot product? Dot product is 0.5 to minus 1 3, and it is, as it should be, it is actually the value of x components, because we have chosen y to be such. If we can choose y to be anything in this current formulation, since I have computed thetas based on this particular y, so I would not be making this change here. But you can be rest assured that it would, and I can actually like stop printing here, which is why it is giving zeros. But you can be rest assured that regardless of what your y is, we can compute dot products like this. But this, despite trying to perform some neat coding, this has still resulted in around 15 lines, which does not appear I won't comment it doesn't appear as good, but if we can actually write the same thing more simply, and many of you already know how we can write the same thing more simply by using sum functions and things like that. And this is what we would be doing next. So first of all, we actually performed a repetitive task using loops. And now what we would be doing is getting rid of some loops. We won't be getting rid of the outside loop, uh, because that is quite natural that we even if we have to perform it manually, or if we have to think about it, so we do want to make this selection. So for loosely speaking, for selection, loops are all right, but for performing the actual operations, if we use functions or dot product functions, or actually matrix multiplication, then that makes our job much easier. So now we would be performing dot product using common MATLAB functions. Now we'll see how easy it actually becomes. So let me call this DPF, so dot product using functions. Once again, I'll just actually initialize it into a zero vector. I would be looping once again, just like before, but now for computing the dot product, I would be using just a single line of code, and I would not actually be using this formula of magnitudes, but I would be using, let me also state it here, that u dot v is equal to u1 v1 plus u2 v2, and actually it would be plus u3 v3 plus so on till un vn for n dimensional vectors. But right now we just have this. So I would actually be, so I, what I want to do is I want to, how I see dot product is it's the sum of element wise multiplication. So we have seen how element wise multiplication goes. So x I get a particular row. In the first iteration of this loop, it would be first row, then it would be second row, and so on. Then I perform element wise multiplication. How I perform element wise multiplication is actually using this dot equal to this dot asterisk operator. So this would be doing the element wise multiplication or element wise product, and then I also have to sum it, right? And our job is done. Let me also print dpf now. So other than writing all this code, also being cautious that we don't make an error in between, maybe we actually choose a wrong index and things like that and end up with a buggy code. This is so simple that it's actually difficult to make a mistake here. And I should also stress that replacing loops with functions or matrix multiplication, the only advantage isn't just less lines of code. Yes, that is one consequence of it, and it sometimes or a lot of times this smaller code is more interpretable, but it's also most of the times more computationally efficient. So if you have to actually loop over, say, a million rows, versus using this code to perform the uh, same operations and reach the same result. So this would be much faster than the for loop, and the reason for it you will probably uh, find in the coming years, specifically if you take some more courses in programming. So as we see, DPL gives us this response, DPF gives us this response, and and both of these responses are identical as well as in line with that intuition behind what a dot product is. And lastly, I would be doing dot product and using vector multiplication. So what is, I think I should maybe also help with some, I think we can refresh the uh, vector multiplication a bit. Let me get some pen. So we have already seen, so let's say that we have x1, which is 1, 2, 3, and it has size 1 cross 3. And I want to multiply, so, and I have another vector, which is 4, 5, 6, and this has dimensions or size or shape 3 cross 1. So based on what you should already be knowing of how matrix multiplication works, the output of this multiplication would be a 1 cross 1 vector, or actually a scalar. And how we would be obtaining it by performing this vector multiplication, how we would be computing is it is actually 1 multiplied by 4 plus 2 multiplied by 5 plus 3 multiplied by 6, which is exactly what we want to do. But one caveat is that instead of having this vector, what we typically have is actually 4, 5, 6, which is also a 1 cross 3 vector. And based on some basic linear algebra knowledge, we know that we cannot actually multiply these vectors. So what we do is we use the dash operation, or this apostrophe, which actually stands for transpose. And what transpose does is that transpose converts a row vector into a column vector as we want, and vice versa. So I'll clear these drawings. All right. So now we would be actually finding the dot product using vector multiplication. Once again, like earlier, I'll be initializing this dot product for I. And now, instead of even using this sum, what I'll obtain is, so what is this? Let's assume that I am just on my, I'm just starting this loop. So I would be actually 1. So this refers to this row vector 0.55 of dimension 1 cross 2. And I want to multiply it with a column vector which is equivalent to y and which has shape 2 cross 1. So I'll be multiplying it by y, but y is actually 1 cross 2. So what I'll do is take its transpose, and that will actually result in both the element wise product as well as the uh, the summation, based on how vector multiplication works, a matrix multiplication works. So I'm done with that. And now we see all these three methods actually end up giving us the same answer. And with this, we are done with first part uh, of our tutorial. All right.